Youth Magazine states that the average age of its readers is 28. This can be important information to a company that produces products for young adults and is considering doing some advertising in the magazine. To test the claim of the magazine, set up the null and alternative hypotheses and do a type 2 analysis on sample sizes of 100 if the real average ages turn out to be one of the following: mu equal to 26, mu equal to 27, mu equal to 29, or mu equal to 30. Okay, the first thing we'll do is set up the null and alternative hypotheses. They're claiming that the average age is 28, so my null hypothesis is to assume that that is true. So the average age we will assume is 28. The alternative is that it is not 28. To run and this is a two-tailed test, but to run a type 2 analysis, we start the procedure out as if we were just running the test itself. Want to look at the sampling distribution, make sure we've got all the values we need. The center would be, since we're assuming the average be 28, would be 28. The standard error in the problem, we're given that the population standard deviation sigma is equal to 6. And the sample is of size 100. So that would be 6 divided by the square root of 100. 6 divided by 10 is 0.6. Also, we are given that alpha is equal to 0.05. This is a two-tailed test, so we will split alpha for both ends, putting 0.025 on the upper end and 0.025 on the lower end. That would give us z-values of negative 1.96 and 1.96. So those would be our decision lines. And we would have a rejection rule. Reject h sub 0 if z is less than or equal to negative 1.96 or z is greater than or equal to 1.96. And if we were just doing a type 1 analysis test, we'd stop there and go ahead and get a sample of size 100, find the test statistic, the z-score of our sample average, and compare it to the critical values of negative 1.96 or 1.96, or find the p-value. But we're doing a type 2 analysis, so we want to change this rejection rule into a decision statement. And we also want to make our decision statement relative to x bar, not to z. So what I'm going to do is I'm going to substitute what z is. It's x bar minus 28 in this case, divided by 0.6. So that would be less than or equal to negative 1.96, or x bar minus 28 divided by 0.6 is greater than or equal to 1.96. And then I'm going to rewrite the rejection statement, reject h sub 0 in terms of x bar. So that just means solving for x bar. In that first inequality, I'll multiply both sides by 0.6 and add 28. So I will get x bar, reject h sub 0, if x bar is less than or equal to 26.82, or, same thing here, x bar, multiply both sides by 0.6 and add 28, greater than or equal to 29.18. And then we get, if we don't reject, we're going to go ahead and say that we accept h sub 0. We'll be claiming that it's true. So that would mean that x bar is between the 26.82 and the 29.18. So this becomes our decision statement. Every sample size has its own decision statement. So if I'm going to be taking samples of size 100, I'm going to do my analysis on this decision statement. So let's look at different values of mu. Suppose mu is actually 26. Now, they've claimed it's 28, but suppose in reality the real average age of the readers is actually 26. And the type 2 error question is, what is the probability that I will accept the null hypothesis stated as given, claiming that the average is 28? What is the probability that I will accept that null hypothesis based on my decision statement, and then the real average turns out to be 26? What's the probability of that happening? Well, the only way I'm going to accept the null hypothesis is by getting a sample of size 100 and the sample average being somewhere between 26.82 and 29.18. If the real average of the population turns out to not be 28, but 26, what's the probability of that happening? So let's see. Well, if the real average turns out to be 26, what's the probability that my sample will lead to a sample average between 26.82 and 29.18? Well, what's the probability of being in this interval if the real average is 26? And that would be just the area under the density function above the interval, as it always is, and that's a normal distribution. So beta actually turns out to be, the beta probability is finding this area. Now again, I'm running a test on mu equal to 28. But in a type 2 analysis, I'm asking this question. If the real average turned out to not be 28, but it turned out to be 26, in other words, h sub 0 is wrong, the average age is 26, not 28, what's the probability that my sample of size 100 would lead to a sample average that, based on my decision statement, I would accept the null hypothesis and therefore make a type 2 error? Well, the probability that my sample of size 100 would give a sample average in the 26.82 to 29.18 interval is, when the real average is 26, this area that I've just shaded. Now what do I do to calculate that? Well, I need the z-score of the 26.82 and against the 26 divided by 0.6. And that turns out to be 1.37. Now, what about the other side of the interval, the 29.18? Again, subtract 26 divided by 0.6. This turns out to be, if I do this calculation, this turns out to be 5.3. 5.3 is 5.3 standard deviations to the right. Well, we know the empirical rule says that almost all of the values in a normally distributed data set is within 3 standard deviations. That's why our standard normal table doesn't go beyond the -3 and 3. So we're way out here on the upper end. Really, to get the probability, a good estimate of the probability, all we really have to do is look up the 1.37, find the area under that, and then just subtract from 1. So if I look up the 1.37, I get an area to the left based on the table of 0.9147. And therefore beta is going to be equal to 1 subtract 0.9147, which is equal to 0.0853. So my beta probability is 0.0853. So if they claim that the average is 28 of their readers, and I go in and get a sample of size 100, calculate the average on the sample, and use my decision statement that I created for samples of size 100, then I would have an 8.53% chance of making a type 2 error. In other words, accepting the null hypothesis and therefore being wrong. That the null hypothesis, the average age is 26, not 28. On the other hand, talking about power, the power of a sample of size 100 is the 91.47%. Again, if I go in and take a sample of size 100, calculate the average on the sample, then there's a 91.47% chance that I will reject the null hypothesis if the real average is 26. In other words, that I will correctly reject the null hypothesis. The null hypothesis is not true if the real average is 26, and there's a 91.47% chance that a sample of size 100 would lead me to reject it, therefore correctly reject it. But I've got an 8.53% chance of making a type 2 error. Okay, let's go ahead and try another one. Let's look at calculating the type 2 error probability if the actual average turns out to be 27. Again, if the actual average is 27, the null hypothesis is wrong, and therefore if I accept the null hypothesis, I will have made a type 2 error. What's the probability of that happening? What's the probability that I'll get an X bar in my acceptance interval, somewhere between 26.18 and 29.18? If the real average is 27, what's the chance that I will be in the 26.82 and the 29.18, my X bar, would be in this interval? What's the probability of that happening? Well, it's the area under the density function above the interval, so my beta value would be this shaded region here. And to find that, I'm going to have to calculate z values for the 26.82. This time, where the center is at 27, and I get a value of negative 0.3, and then on the other end here, the 29.18, subtract 27 over 0.6, and that gives me a value of 3.63. So I'm still on the upper end. I'm still off the chart there. I'm pretty far out to the right. So really, I think I can calculate beta as a good estimate of it by just going to the left-hand point down at negative 0.3 standard units to the left, and my table value gives me a 0.3821, and therefore beta would again be equal to 1 minus 0.3821, which is 0.6179. So beta is 0.6179. What this tells me then is that if I take a sample of size 100 and run this test, testing against the 28 as the assumed average age, there is a 61.79% chance that I will accept the null hypothesis if the real average age turns out to be 27. In other words, the real average age turns out to be 27, the null hypothesis is wrong. So if I accept the null, I will have made a type 2 error. With samples of size 100, when will I accept the null? I'll accept the null if the sample average is somewhere between 26.82 and 29.18. Well, if the real average is 27 and the null is wrong, what's the chance of that happening? It's the 61.79%. The probability that X bar would fall in that interval with the real average being 27. What is the power? of the sample of size 100 under this condition, when mu is equal to 27. There's a 38.21% power. Power meaning to correctly reject. I'd have a 38.21% chance of rejecting the null, and if the real average is 27, I will have done so correctly. So the power is the probability to correctly reject the null. And the sample of size 100 doesn't have much power if the real average is within 1 year of the 28. It had a lot more power if the actual average age was within 2 years. When we look up there again at mu equal to 26, if the real average turned out to be 2 years away from what was assumed at 28, then a sample of size 100, 91% of the time would correctly lead to me rejecting the null. But it loses power the closer I get to the 28, and at 38.21%, the sample size 100 is not very powerful in getting the rejection. Let's go ahead and try another one. Let me do the 29. Suppose mu is 29. The null hypothesis is wrong. 29 is much further up here. And if mu is 29, what's the probability that my decision statement based on a sample of size 100 would lead me to accept the null? Well, the probability of being in the interval from 26.82 to 29.18, what's the probability of being in this interval when the real average is 29? Now that's interesting on this one. I'm on the other side of the 28, but again, with samples of size 100, my acceptance interval is always still the same. I'm going to go ahead and calculate the z value for the 26.82. This time subtracting 29, dividing by 0.6, and I get a negative 3.63. So the lower end of the interval is now sort of off the chart to the left. And let's see what happens with the 29.18. I'm going to subtract the 29 divided by 0.6. And that turns out to be positive 0.3. So looking at this, since my left end of the interval is so far to the left, I really just need to look up the table value to get beta. And I don't need to subtract from 1 in this case. So looking up the table value here, looking at 0.3, I get beta is 0.6179. Now that's interesting because looking at 27, which is 1 year less than 28, and 29, which is 1 year more, the power to correctly reject the null hypothesis doesn't change. I'm within 1 year of the 28. The probability of making a type 2 error doesn't change, 61.79%. Again, I'm still a 1 year error off of what was hypothesized. So in this case, it doesn't change. If I go on and look at mu equal to 30 and do the same thing, I will find out that beta, and you can try to do the calculations on your own here, but I would find out that the beta would be 0.0853. Again, I'm 2 years off on the upper end.
So there's a 2-year error based on what the hypothesis test says, and 2 years on the upper end would be like 2 years on the lower end. It's still the same sort of probability of getting that type 2 error, and the powers are also the same. So I hope this helps as far as how you would conduct a type 2 analysis on a two-tailed test. If I didn't like any of these values, for example, my probability of making a type 2 error being within 1 year of the 28 may be a little too high, the power's a little too low. What I can do ultimately, going into the next section, would be to calculate the sample size that would give me the error probabilities that I want, that I can live with, and give me the sample size that produce a decision statement that would make that work. And that's something we'll look at in the next section.